So this is the notes for your third assignment, which is a very broad-based statistics assignment dealing with all the displays and the concept of standard deviation, how to calculate outlier boundaries, and the concept of the shape of displays. So this will take a little time, and I'll tell you exactly what I want you to do. I want you to do this page. I want you to do the random graph problems, which are well into this packet, and then one outlier calculation. And as we come upon those, I will show you those. You might want to use the calculator soup. What a name for a descriptive stats calculator. To do the page, this page here, as it goes very quickly. Just know that the calculator soup does not do the population variance and standard deviation. It does a sample, so I don't think I had that written in when I scanned it, so you can write those in. And we'll get to what the meaning of standard deviation is in this packet. But for right now, you can just calculate those, and then the square of standard deviation is the variance. So this page is for you to do, and I'm going to move pretty quickly through this to explain all of these things. So circle graphs are very important, and these are the ones we need to circle: 4, 7, 8, 9, and 11. And number 4 is the main deal. Circle graphs demonstrate the relative size of certain data intervals and categories compared to the relative size of other data intervals and categories. And pretty much this table up here is what you use to make the circle graph. Now, where did I get the 1, 1, 7, 7, and the 2? That's your original set of data on the first page. So all these displays are working off the set of data that's coming from the first page, which is right at the top here. And then the percent probability, you just simply divide by the total and then come up with a percent. So this is about 5.6%. Keep in mind that we're rounding, so as you actually fill in the rest of these, it may not quite add to 100% because of the rounding. So this will be 38.9. This will be 38.9. And then this will be 11.2. And actually, when you add these, you'll get 100.2%, again, because of the error in the rounding causes a little bit of error. Now, the sector angle, basically you take the 1/18 times 360 to get the part of the whole 360 degrees that you would need to shade. Very simple stuff, but you need to know this because in your random graph problems that you'll be doing, you have a circle graph that isn't so easy to work with. It's the same idea. It's a percent of a whole amount. So the whole amount is 18. That's what this value is everything. So I think on the random graph problem you have, it's your total expenditures. That is the number that's everything, the whole amount. And then, so if you're going to complete the circle graph over here by labeling, you could do the 70s and 80s, the 90s right here, and then the 40s and the 60s. So I had the angles drawn, and then you just need to fill them in. So that is a circle graph. Very important that you understand the whole amount of something is going on, and then you can figure the probabilities, and you can figure the sector angles to draw on the display. Box and whiskers. So 1, 2, 5, 6, 8, 10, and 12 are the important ones. The real important ones are a box and whiskers can be used to demonstrate dispersion of data, so how spread out your data is, and then the quartiles can be seen. So on this, the 40 is your lower extreme, and then from the front you can get all of these, so 75, 80, 87, and then 95 on the upper extreme. So from the first page, you would just simply look those up, and those are the boundaries. So The lowest group of data, when we chop it into fourths, is from 40 to 75. Then 75 to 80, then 80 to 87, then 87 to 95. That's if we don't throw the outlier away. Now, what some computer programs do is they throw it away, they put an X there, and then they go to the next. So 68, lower extreme here, would be where the dot is, and then connect to the box. So be aware of that, that sometimes you see it drawn that way also. Okay, histogram, very important display. So 2, 4, 5, 8, 9, 10, 11, 12, a lot of them. The real biggies are 4 and 8, especially 8. Scaling on the x-axis of histograms has to be in intervals, whereas a bar graph, it's just categories. So that's the big deal, is that the scaling there has to be in intervals. And then you just simply count the frequency. There's 1 in the 40s, 1 in the 60s, 7 in the 70s, 7 in the 80s, and 2 in the 90s. It's that simple. But the scaling is the big deal there. Pareto chart. So this is to make a point. The big ones are, number 1, to order the frequencies from greatest to least. Probably shouldn't have started 4, but yes, you can also demonstrate the relative size. It's to make a point that whatever the 80s and 70s are representing, they're way out pacing those other intervals, whatever that data represents. So just ordering from greatest to least. So then this kind of becomes a bar graph rather than a histogram, because you're really just kind of categorizing down in the x-axis there. That's what a Pareto chart is it just takes those bars and goes from greatest to least. Pareto chart. And then the O guys. So this is about the accumulation of the total number of data elements. So a much better way to use this, let's say you're a business and you're trying to keep track of cumulative expenditures. And OGIVE is a great way to do that. So how much total money have we spent through, let's say, each month of the year? And OGIVEs are extremely useful when when the accumulation of something matters. So all this is doing, if we took get the box or the histogram back here. So it's just, we have 1, and then 1, there's nothing in the 50s, and then there's 1 in the 60s, so you do 1 plus 1 is 2, and then 7 in the 70s, so after the 70s you have a total of 9, and then 9 plus 7 is 16. So it's just adding the cumulative total of each of them. Actually looking up here is a whole lot easier. So after the 80s, right there, you have 16 out of the 18 of the total. So it's just to keep track of a total something. This isn't the greatest one to demonstrate the number of numbers. Usually you're trying to demonstrate some total, like, again, money spent through a particular month in the business year. Stem and leaf. You've heard this, and I'll quickly put these in. So 68, and then 72, 72, 4 75s, and a 79, and then an 81, and then 83, 2 84s, and 87, 2 89s, and then a 92 and a 95. It amazes me how many people just get totally floored by that. So you're just basically, in any stem and leaf, you have the last digit, and however the number is represented is the leaf part, and then the stem is the rest of the number. In the idea is 3 and 4, you can tell what the exact data elements are, and it also demonstrates the relative size of, if you turn it this way, you kind of got the histogram in a way. Useful if it's the small set of data, it's useful. So, if you're a teacher and you're trying to write down all your test scores, let's say the class of 15 kids, and you're trying to write them down, this is a useful diagram to use. So small set of data for this, and then you'd see the individual data elements. That's the big thing. All right, so here's your random graph problems that you need to do. and you need to do these to the best of your ability, and you might have to think a little bit. This is a weighted average on number 1. So you need to consider this is 5 here, this is up to 8, this is up to 11, back down to 6 here, this is 3 and 2. So that is a weighted average, and you need to go back on, okay, what does it mean to do weighted average? Okay, and then more questions on problem 6 here. 22% is the percentage that goes with housing, and 17% is the percentage that goes with food. You can't see it very well on that, so I had to write it in there. You need to figure out the total amount. Remember, that's the number that's huge. What I don't have here is I don't have the whole column like you saw it on my original problem. So the first thing to do, what's the total amount of expenditures? And I'm going to let you toil a little with that, because that's the big, and don't tell me you can't see the values. There's a way to figure it out by using the fact they spent $10,780 on housing, and that's 22% of the total. So 0.22 times X equals 10,780. Then you can figure out what the total is, and then you can go from there. And then some more here. That fact that's whiter has nothing to do with anything. All right, so calculating outlier boundaries is the next thing, and you have seen this. And so it is important, you're going to have to use calculator soup here to put these in and get the first quartile and the third quartile. Make sure that you look those up correctly. And I'm going to do 1 and 2, and I'm going to leave number 3 for you to do. But you will have to use calculator soup or your graphing calculator to do this. Lower boundary calculation. Okay, so you do also need to do, and I didn't put room for that in here, you need to do your interquartile range calculation minus Q1. And let's see, 102.5 minus 69 is 33.5. So you need to do that also. So the lower boundary is simply 15 minus 1.5 times 14, whatever that is. And then the upper one is 29 plus 1.5 times 14. So it's the lower quartile minus 1.5 times interquartile range. Upper boundary is 29, the third quartile plus 1.5. So when you do this, you get 2 answers. Now you're not done here. This just drives me crazy when I put this on a quiz. You have to apply this to the set of data. Are there any numbers less than -6? Answer no. Are there any numbers more than 50? Yes, 80 is. So 80 is an outlier, and you can spot that usually without having to do these calculations. But same way on 2, I see 500, that's way out of line. Way, way, way out of line. Okay, so 69 minus 1.5 times 33.5. And then 102.5 plus 1.5 times 33.5. And that gives 18.75. You'll get some weird values, 152.75. So apply that to the set of data, and yes, 500 is an outlier. So if there's nothing less than 18.75 or more than 152.75, there are no outliers. Number 3 is for you to do. Okay, so that takes us to the shape of distributions. This is also very simple. So you have skewed right, symmetric, uniform, or none. Skewed left, skewed right, symmetric, uniform, or none. So symmetric just means that it looks like what's called a normal curve, or even better, you can take a line. So if I grab my ruler here, and you can cut it into 2 fairly equal halves. This is fairly symmetric. Not perfect, but it is fairly symmetric. What's another one that's symmetric? Number 4. For certain, I can cut that into 2 equal halves. Also, number 4 is uniform. So uniform means you're, just what it says, you're at some consistent level going across. And then number 6 is none of the above. Just get that one out of the way. And the rest are either skewed right or skewed left. So if you remember me talking about outliers, outliers are data values that lie far to the right or far to the left and tend to blow up the mean in either direction. So wherever you see the tail, that's where your outlier is. So this is going to be skewed to the right, meaning that these outliers that are more to the right here, when you go to do an average, they're going to throw the mean off and pull the mean to the right. It's just where the tail is. So this one is skewed left. So because you have outliers to the left, when you go to do the mean and the standard deviation, it's going to pull the mean to the left of the median, and that's not a real good thing. Same way here, when you look at this, you see some tailing off to the right. So we're going to call this a skewed right distribution. It's wherever the tail of the graph is. And if you have tailing in both ways, like this one, then you don't. It's neither, okay, and possibly symmetric. All right, standard deviation concept. So this is the best one I can come up with. Notice that you can do this actually without a calculator. So if I average all those, I have 350s and 3 100s, 75 is the middle, is the mean and the median. And the standard deviation is 25. Now, what does that mean? That means that most of your values lie from 50 to 100. Here, all of them are exactly 50 and 100. And I use this as a standard example just because people then get the idea, oh, we subtract it from the mean and we add it to the mean. And here it's a perfect either or. Now, you're never going to get that in a realistic set of data. The point with it is you subtract it from the mean and you add it to the mean a particular number of times, usually just once, although it can be twice and sometimes 3 times if you're trying to get outliers. And there's something with normally distributed data that you do it once, twice, and 3 times. So number 2, a certain data distribution has a mean of 72 and a standard deviation of 12. Between what 2 boundaries would most of the data lie? So you're subtracting and adding 1 time. So 60 and 84. It's really easy to add and subtract. Nothing hard about it at all. Problem 3, so you have now the 2 values, 22 and 64. How do you get the mean? Well, you add them and divide by 2. So this is 86 over 2. So 43 must be the mean. And then you just think about, so 43 minus what is 22? That would be 21. And then 43 plus what is 64? That would be 21. So the standard deviation is 21. So that's just like working backwards. That's no big deal. Another way of considering outliers, so I've talked about this. So we need to go 3 times. And it's much easier than the having to do the problem that you did earlier. So 36 and 108 would be the boundary values less than 36, and more than 108 would be the boundary values for outliers. So I think on your quiz I might have done that. Somewhere I did that. And then the end here, so standard deviation and displays. So we need to rank these in order from least to greatest. So the least spread out to the most spread out. considering all parts of the graph. So this is top one is the most spread out, and then this is less, and this is less. Okay, so here, notice that little square there. So that is an outlier, and they left it out of the calculation and then just started the box and whiskers at the next value. So this kind of goes left to right. We're considering standard deviation. What's the least spread out to the most spread out? Okay, and then this last page in this packet. So when you have these, I guess these stem and leaf, you want to look at, so this is the least spread out here because all the data is really close to the middle stem. And then I'm going to say this first one is the most spread out because the data is the most removed from that middle stem. And then here that's number 2, so it kind of goes backwards. So this is the least spread out, and then that first one is the most. Same idea applying here. So most of, you have the tallest middle stem there, so that's the least spread out. And then it seems that this one is more spread out than this one. The points are farther away from that middle stem. The numbers are farther away from the middle stem. Here, same thing. This is the least spread out, and I would say this is the most because your mean is right here in the middle. It's not even part of the data set. So definitely that's the most spread out. And then curves that look like normal curves. This is the least spread out, and then the green is number 2, and then the blue is number 3. All right, so that's that packet. You have the first page, you have the 8 random graph problems, and then the 1 calculation for outlier boundary problems to do.